Let's suppose that x and y are numerical. Do x and y have anything to do with each other? Let's try to pose the question in a more precise way. You've been collecting records, and so you can form a joint probability table between x and y. So we can say in an absolute sense, in a prior probability sense, what degree of certainty do we have about x? If x takes on the values x1 or x2, we can ask what's the probability with which it takes on those values. So from the table here, we know we can just evaluate those numbers. They're just 0.29 and 0.71. Now, let's suppose that we know that y is stuck at y1. Does this make us more certain at all about what x is? Specifically, what's the conditional probability that x is x1 or x2, given that we know y is fixed at y1? Well, again, we can just directly evaluate it from the table. It's 0.16 and 0.84. So it seems that knowing that y is stuck at y1 has told us something about the value of x, right? Intuitively, we know that. It caused the probability to skew a little bit to one side, in this case, towards x2. It turns out there's an expression to measure the degree of skew of a probability distribution. This expression is called entropy. Specifically, let's suppose that a random variable x takes on the values x1, x2 through xk. The entropy for the probability distribution of x is labeled h of x, and it is defined as minus p1 times log of p1, minus p2 times log of p2, and so on through pk. Otherwise written as minus 1 times the sum of pi log pi. Now the base of the logarithm isn't necessarily important. If the base is base 2, then the units of entropy is called bits. If the base is e, then the units are called nats. Traditionally, in computer science, we use base 2, but it's not really super important. Now, to see what's behind the expression h of x, and why this formula was chosen over other options for formulas, and much more details about information theory in general, see the instructor's notes.